Marvelous, darling. Marvelous. Marvelous. All right. All right, this is the last. Oh, man, it breaks my heart to miss you guys. This is it. This is the end. Oh, yes, I look forward to it. I look forward to it. All right, what we're going to do is we're going to be working with an induction coil, and I want to describe, and they changed the world. I mean, induction coils, everything started the first long-distance communication, telegraphs. It allows us to generate electricity and send it long distances. I think the last time I told you about why Mr. Edison lost, because Mr. Tesla and Mr. Westinghouse came up with the transformer that basically allowed us to transmit energy over long distances. So the idea behind this induction coil is you have a current running through a wire. All right. In this case, there is no current. Here's a piece of paper with iron fillings sitting on top of it. No current. The fillings just sit there. The filings, I should say. If I then run a current through the wire, you will then see these filings start to line up in concentric circles, because now there's a magnetic field. That concept alone changed the world. Current, magnetic field. So we call it the electromagnetic force, EMF. All right? So these guys did all kinds. This guy Oersted did an experiment way back. He took a compass, wire, no current, the compass is pointing north. With the current on, the compass now lines up opposite of, away from the north, because I now have a magnetic field that's much stronger than the Earth's magnetic field. Now we call it an induction coil because it's that. You have a wire and you have a magnetic field. To make that magnetic field even stronger, what do? I wrap it around. And I put a metal core in there that's going to force those magnetic field lines even stronger. So that's what you get here. You get a length of wire. That's why we call it an induction. Induction because you're inducing a magnetic field. Coil because you're wrapping it around like a coil. That's the basic principle. All right. All right. So it's a passive element. It consists of just a coil of wire, and there's all kinds of them. We have toroidal ones that go around rings. You can have center tapped ones that have an iron oxide in the middle of it, and you have the good old transformer. All right. Transformer here, with you just have this is a center wound transformer because you got the coil sitting on the center. So the symbol for a coil is exactly that. We just use, this is the symbol. L is going to be for the inductance. V of T is going to be the voltage. I of T is the current. And again, we have this, just like we had for the capacitor, I through C with C dV dt. Here we have, in this case, we have the voltage across the inductor is equal to the inductance times the rate of change of the current that's going through it. Okay? So that's the basic idea. And see, these were some of the early transformers. If you want to see a transformer, you could just look right out the window. It's sitting right on that gray can. It's sitting right up there. Right there. That's a transformer. That's stepping down a high voltage down to a lower voltage so you can get 110 volts coming out of the wall. All right? So this was some of the early transformers look like this. Yeah? You'll have, some people are on different grids that we call them. So like there's a grid here that runs from, there's a nuclear power plant out in Limerick. That power's down here. Some are interconnected, some are completely disconnected. Okay? Yeah. That's how like the largest one is the TVA, Tennessee Valley. They, millions of customers. I mean, they're using major hydroelectric stuff. That was about a relay, one relay, which is basically almost like a transformer, tripped up by Niagara Falls. And the whole domino effect all the way down. All these other breakers started tripping. Yeah, big time. Yeah. Yep. One little electromechanical switch. And these were some of the early Faraday. Michael Faraday worked on these kind of things. And this is one, you'll see this. This was an audio transformer. This stuff sits in all your little radios and phones and all that kind of stuff. I mean, they're all over the place, these guys, all right? Some of the stuff you can do with it, they figured out you could do mechanical work with it, all right? So here's a lever arm with a weight on it. If I powered up that coil, I can pull that weight up. So I can physically now use electricity to do mechanical work, all right? And you'll see that is done if you go down by Passyunk Avenue and the junkyards down there. There's a big electromagnet picking up scrap metal, all right? Oh, your doorbell. So you can pick up all kinds of metal filings with these things. So now I can start having it do work. And if you look in some of the older doorbells, this has 2 coils of wire, and basically there's a spring that keeps this guy away. Once I energize these coils, this will start going like this and start hitting this. And if I send a current through there that's sinusoidal, it'll go bing, 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 and that's how you hear your doorbell starting to go off. There's a lot of neat stuff in there. Your starter, everybody who has a car has a starter in it. And inside that starter, you've got a huge coil. You've got these big cables coming in here because you've got to really boost up the power that's going to go into the starter. So if you look in your car, I have my battery, turning the key, down through here is a coil, and then we go to our starter, which then turns the motor, gets your car started. You can generate electricity. This is how, if you take a coil of wire, and here I have a permanent magnet, and as you move that thing, if you change the magnetic field, a time-varying magnetic field, you'll generate a current in that coil of wire. You see all the little generators out there that these guys have on their trucks? Little generators? What you have is you have a gas moving a rotor. And on the out, that's called a rotor. That's part of a machine. So you're rotating this around, and then on the outside part is a stator, which all it has is little coils on it. So as soon as I move that magnet past that coil, what happens inside that coil? And induces a current. So now the guy can cook, or he can turn on a light. And that's why you see those little generators out there, and that's what it's doing. It's moving that magnet. Now, in this case, we're just moving a magnet in and out, but there, you're rotating it, and it's inducing a current, and all those little coils are on the outside, and that's how you generate electricity. So simple. I think I have a, oh, shoot, I have a video I could have showed. Did I show you the video of the motor last time? I think I did, yeah. All right, so the idea here is you have these huge, this is like the Hoover Dam that's out in Nevada. You have these jets, you've got this lots of water back here, and then it comes out down here, and you have all these turbines that are sitting in there. Those turbines are just moving, moving around. You generate tons of electricity comes out of there. So what you start off with is usually a power station, transformer, send it down through a transmission line, step it down, and then you bring it back into your houses. All right, so you go low voltage, lots of current, high voltage, low current, back to the stuff that you need for your house. Okay? That's basically the idea of how it works. Yeah, typically you have coming out of that wall outlet is a sinusoidal, and it's running at 60 hertz. All right, so it's repeating itself. All right, sinusoidal. Typically you'll have a 15 amp breaker on there. That's what your usual breakers are. So you're getting 110 to 120 volts, peak to peak, sinusoid, and you can, it depends on what you plug in here. Like it depends on how much of a load I want to do. If I plug in a motor in there, I could be drawing up to 10, 12 amps. If I plug in a radio in there, I'm drawing milliamps. All right? But it's there for you. Okay?
What happens to the excess when you're drawing a little bit?
It just depends on how much you need to draw. That load can vary. All right? So if I have like I put a radio in there, I'm going to be drawing milliamps. All right? If I have a motor, I can be drawing amps. But there's no, I think your question is, why aren't I getting all of it all the time?
Right.
called the load. The radio itself only needs a little bit of electricity. So that's why you pay for different. I walk around my house, I turn lights off. My kids leave the lights on all the time. Because I'm drawing more of a load. That little meter that's sitting on the outside of my house, with all the lights on, is spinning fast. And the money's coming out of my wallet. So I ain't gonna run and turn the lights off. All right? I mean, it's simple as that, you know? But it depends on how much load that you draw.
Well, what is stopping it from all the load coming in at once, is what I'm asking, I guess.
You're asking, like, where's the break?
Yeah.
Yeah, I mean, you can supply up to 15 amps, and then a breaker will trip. So it depends on, like, this device here is only using a little bit of current. Now, there's a reservoir of stuff out there. Think of it as you're controlling a valve, all right? When I plug it in, that radio only needs a little bit of electricity to work.
So each plug is effectively...
Each load will take, that's why we call them loads. That's because you're loading down the system. Radio's going to load it down just a little bit. A motor will load it down a lot, but the reservoir is there for you. Typical example, I have a sauna in my house. Literally. I mean, it's a hot sauna. I'm in there the other day, all of a sudden, it shuts down. Huh, I'm in a good sweat. You know? So now I go out and I hear a hairdryer going. My daughter turned her hairdryer on. So at that point, you had too much of a load, trips the breaker. All right? So that's that idea. But yeah, I understand what you're saying. Where's the break? It's how much load that you need to absorb. All right?
Does it also depend on like the circuit inside the radio? Like they would have internal resistors?
Oh yeah. That's exactly it. Yeah.
I
Yeah.
think that's what he was
Yeah. All right, so the early energy transmission you have, do you have to do that up here? Do you have to do that? People trying to watch and listen? Thank you. So you have a transformer that in this case has a number of turns on one side and another number of turns on the other side, so I can step up or I can step down either way. All right? And that's what you see in these transmission systems that are there. You can think of it as, you guys ride a bike? You have a gearing system. You can gear it up so that I can take one turn to maybe a half a turn of the wheel, or I can maybe take one turn and I'll get 5 turns out of the wheel. Same idea as a transformer. There you're just doing it mechanically with these gears. That's how that one works. And as I mentioned, the early telegraph systems, that's where you had these guys, and I built one. There's a little coil right there. There's a key that you tap. You run the current goes through here, and it'll pull that coil down. So you can just sit there and tap and start communicating. And that was one of the early electronic systems. And then Samuel Morse came up with a code for it. So that was the idea. You had these early telegraphs. The electric guitar works that way too. I mean, that's how an electric guitar works. You have magnetic pickups. These are all metal strings. I have a magnetic pickup that sits right underneath that guy. So that's what you see here, is these are the metal strings. There's a magnet here, and underneath is a coil. So as I pluck this string, I vary the magnetic field. That then goes down to the coil, and then I run that to an amplifier, and bang! You get, that's how you get an electric. So you have here, the pickup is at rest. As I pluck it, I start varying the magnetic field. That's going to generate a current inside that little wire that's in that coil there. All right, so that's my little spiel on inductors. So now let's get to doing some relationships. All right, so the current through inductor is given as an integral relationship, and that's one of the reasons that we're studying integration. All right, we have the current through the inductor here is equal to 1 over the inductance times the integral of the voltage across the inductor, and then we divide that by the inductance L, and then we have what's the initial current at T equals 0. Okay? And the power stored in an inductor is simply 1/2 the inductance times the current squared. And let's look at some. All right, so in review, there's 3 circuit elements that we've studied in this course so far. Resistance, its units are ohms. It's given by Ohm's law. The current is the voltage divided by the resistance, and the power is equal to the voltage times the current, or what we call I squared R. The inductance is measured in henries, and it's equal to V is equal to L di dt, or I is equal to 1 over L, the integral of V, plus this K1, which is the initial current at T0. And then we have, that's the power. And then as we did last time with you, we did the capacitance, it's farads, it has this integral relationship, and so forth. All right, so let's do some examples at the board. All right, so now we're going to have a current through an inductor is given by 30T. So we have 30T e to the minus 2T. All right, and what we want to do is we want to determine the voltage across the inductor and the power at 1 second and the energy stored at 1 second. All right, so what we can effectively do is we're going to have L di dt. VL of t is equal to L di L of t dt. All right, so in this case, we have the inductance. It's a 12 millihenry inductor, so it's 12 times 10 to the minus 3 times the derivative d dt of 30 t e to the minus 2t. All right, so let's just look at this term by itself, the 30t. How would you do that derivative? So we're going to take the derivative of 30t e to the minus 2t. How do we work that derivative out?
We start with the we start with the T. No, I would start with the E personally, just because it looks a bit difficult. I would put the E in front of the 2E. I mean negative 2E to the negative 2E.
Minus 2?
Yeah.
Well, the 30 can come out, right?
Right. 30 can come out.
30 comes out. And then we have what?
T squared.
T squared.
Oh no, it'll just be T. Oh, you taking the derivative? I'm sorry.
We're taking a derivative.
And it'll be negative 2E.
All right, so you're going to have minus 2e to the minus 2t,
Yes.
right? And what else? What rule are we using?
Subtract from the exponent?
Don't subtract.
I mean, we'll minus.
Yeah. Well, here's all right. So you have this. Consider this as f1 of t, and this as f2 of t, right? And when you do we have a product of two functions here, right? So what we use the product rule, right? So you have, when I'm taking the derivative of f1 of t, f2 of t, that's equal to f2 of t times the derivative of f1 of t plus f1 of t times the derivative of f2 of t. That's the product rule. So now we have, this is f1, that's f2, or you can do it either way. So this now becomes, so if you're going to call this f1 of t, and this is going to be f1, that's going to be f2. So now we will do this. We're going to have f2 of t, which is going to be e to the minus 2t, times the derivative of this guy, the derivative d dt of t, and then we're going to have plus, and all this gets multiplied by that 30, plus t times d, dt of e to the minus 2t. And I need my other brackets right there. So now the derivative of t is what? Derivative of t, dt of t.
Oh.
Derivative of t. It's just one. Yeah, just one. So this guy comes out to be 30 times e to the minus 2t times 1, and then plus t, and what was, you had the derivative of this before? Yeah, so this becomes a minus 2 e to the minus 2t, and then all that gets multiplied by 30, okay? So in the end, if I factor things out here, I'm going to have 30 times, let's see, I'm going to factor out an e to the minus 2t. 30 e to the minus 2t times 1 minus 2t. That's what's going to be in the end. And then I have to go over here, and I multiply it by 12 millihenries. Okay? So this all gets multiplied by 12 times 10 to the minus 3. Make sense? All right? So that's just running a crank on using the product rule. Okay? And when you multiply all these numbers out and bring everything inside, you'll get that result right there. Okay? All right, cool. All right, then if we need to find the power is equal to the product of the voltage times the current, and then I substitute it in, it's going to be a T equals 1 second, and you'll get end up with minus 0.1978 watts. Okay? And then in order to get the energy, it's 1/2 Li squared. So we know what the current is. It's 30T to minus 2T. I plug in T equals 1, and I'm going to get 98.9 millijoules for that guy. All right, so now, that was a derivative. We did an example of a derivative. Next, we're going to go on to an example of the integration. All right, so now let's do an integration example. Any questions so far? You guys all right? All right, so now, here we have the voltage across an inductor is given by this polynomial here. Okay? So now let's calculate. All right, so we're going to find the current. Okay? The current I of t. So it's equal to 1 over L, the integral. This should be V. On your slides, that should be a V. Okay? Because that's going to be our V. All right, so what we have here is we're going to have I of t will equal 1 over the value of an inductor. For this case, it's 200 times 10 to the minus 3, 200 millihenries. And then we have the integral from 0 to t of, we're going to have 3t squared plus 2t plus the 4 dt. Yes?
So then the voltage is L. The voltage is
Is
L.
V.
So,
V is the voltage, L is the inductance.
oh, then, 200.
L's fixed, yeah, because it's a fixed inductor. But the voltage and the current are going to be time varying. Okay? All right, so now we put, in order to get this integration, this is, I think, 1 over 0.2, which, if I bring it up to the numerator, is going to be 5. And then I have 5 is going to be times the integral from 0 to t of 3t squared dt. And we break it up into the other integral of 0 to t of 2t dt plus the integral from 0 to t of 4 dt. So we've broken it up into 3 different integrals. Make sense? All right. So now what we're going to have 5. Bring the 3 out front. When I integrate t squared, what do you get? T cubed over 3. So this becomes now, this inner one's going to be t cubed over 3. So I'm going to have 3 divided by 3. And then I have t cubed evaluated between 0 and t. Plus, when I integrate the t, I can factor out the 2 here. Integral of t is what? T squared over 2. So I'm going to have 2 divided by 2. And then I have t squared evaluated between 0 and t. Plus the 4. I'm going to get the 4 out in front. The integral of that is going to be just t evaluated between 0 and t. So now I plug that in here, so I'm going to have 5. This is going to be t cubed minus 0 cubed for the upper and lower limit, plus t squared minus 0 squared, plus 4 times t minus 0. All right, so we have 5 times t cubed plus t squared plus 4t. That's going to be what the current is, okay, for all time, for all time.
How do you find out what I of 0 is, though?
For this guy here, I of 0 was given to be 1 amp.
Is it always going to be given?
Yeah, you'll have to know what the initial value of the current is. Yeah, that has to be given. So yeah, you're right. I forgot to add that onto the problem here. So that's going to give me all this up here gets plus I of 0, and that's 1. Make sense? All right, and when you work it out and do all the multiplications and everything, you get that guy. All right? It's right there.
That's it?
Yep.
That's it?
That's it.
Wait, what did you put? Why did you put plus one again? Plus one is from the original?
The plus 1 came from I of 0. Okay?
You just put plus one?
Yeah, because it's this term right here. That term right there.
Okay.
Make sense? Okay. So when I multiply this out, I'm going to get 5t cubed, which is this term, and then I get 5t squared, which is that term, and then I get 5 times 4t, gives me 20t, and then I get the plus 1 there.
Well, you can leave it like that, right?
Yeah, it's just, yeah. Quite acceptable to leave it like that. All right, so now we're going to have the voltage across the inductor is given by 20e to 1 minus e to the minus 2t. The initial current in this case is going to be 0.3. All right. Find the current and energy stored at t equals 1 second. Okay. So, all right. So we turn on the crank here. And we exercise another rule of integration. And I need a little more chalk. All right, so here we're going to have V of t is equal to 20 times 1 minus e to the minus 2t. And we know I at 0, I at t equals 0 is 0.3. So therefore we have I of t is going to be 1 over L, and this inductance has a value 2 henries. So it's 1/2. Then we're going to have the integral from 0 to t of 20 times 1 minus e to the minus 2t dt plus point. Don't forget your initial value for the induction current. All right, so now we're going to use I of t. 20 over 1/2 is going to give me a 10. And then I'm going to have 10 is going to be multiplied by the integral from 0 to t of the 1 dt minus the integral from 0 to t of e to the minus 2t dt. That, and then we add the 0.3 on. Okay? We add our 0.3 on there. All right, so let's get the integral. I of t is going to equal 10 times. The integral of 1 gives me what? The derivative of 1 gives me 0. Yeah, don't let that be your quiz grade, 0. So this is what? That's going to be t and evaluated between the lower limit and the upper limit, right? So I got t is going to be evaluated between 0 and t minus, now the integral of e to the minus 2t. It's minus 1/2, all right, because the integral of e to the at dt is what? 1 over a e to the at plus a constant of integration, right? So in this case, it's minus, and then I have 1 over minus 2 times e to the minus 2t, evaluated between 0 and t.
I'm sorry, I think I left my wallet in here.
Ooh. Who's got the money?
Over there.
Yeah, go ahead and check, yeah. There you go. All right, so we're going to be left with here with t minus 0.
Have a nice day.
You too. Glad you got your wallet back. All right, and this is going to be plus 1/2. And then this is going to be evaluated between, we're going to have e to the minus 2t minus e to the minus 2 times 0 plus the 0.3. So this is equal to 10 times t plus 1/2 e to the minus 2t minus e to the 0 is how much? 1. All that. A max plus the 0.3.
I have a question. Where'd you get the
Go ahead. Okay.
where'd you get the one over two, the front of it, the second line?
This,
Yeah, where did you get
that's right here. Let me go back to the last slide. That's L. That's the inductance. All right? So when we work it all out and put all the numbers in, you have 10t, which is here. I have 5 e to the minus 2t, which comes from here. And then when you work it out, and when you got the 3 in here, you get the minus 4.7 here. Shazam! And then if you wanted to get at t, if you want to evaluate it at 1 second, you just plug in t equals 1. Okay? I didn't get the, how we doing on the clocky poo? Oh, we're good. We're good. Good. All right, here's the one that's a little tricky. Here what we have is a voltage source across an inductor, and this is generating a square wave. So this voltage source goes from 9 volts for 2 seconds, then it goes down to minus 9 volts for 2 more seconds, up and down. And what we want to do is the current and voltage in an inductor. All right, it's 5 millihenry inductor. Okay. So now what we want to do is calculate. We know that the voltage across an inductor is LdI dt. We're going to plot the current, and then we're going to do this using integrals. Okay. So the best way to break this up is that you say, okay, for 0 is less than t, which is less than 2 seconds, we're on this time interval, v of t is equal to how much? It's plus 9. So we're going to have I of t, and now I'm going to have to assume that I at 0 is 0 here. If you're not given it, just assume that it's 0.
Like that.
I didn't put it on here. I forgot. But all I would have to do is, again, all you're doing is you're adding it on out here. You know what I mean? You just add that number to what you get in the end. All right? So I of t is going to equal 1 over L, which is 1 over, this is 500 millihenry, so it's going to be 1 over 0.5. The integral of 9 dt plus I at 0.
Why 1 over 5 again?
It's 1 over L.
Okay.
500 times 10 to the minus 3 is 0.5.
Okay.
So it's 1 over L, which is that guy there. All right? Now, we are going to have to work with this, all right? Because I'm going to need, see, I'm going to find the initial current for this time interval now, all right? So now this is going to equal 2 integral from 0 to t. What's the integral of 9 dt? This 9t, right? So this is equal to what? 18t plus I at 0, all right? And if we assume that this is 0, okay? So it's just 18t. So now what's going to happen here is if I of 0 is 0, I'm going to graph down here. This is 2. This is 4. This is 6. And this is 8. This guy's going to start going like this. It's going to be, and this curve, this is I of t. This curve is going to be 18t. And this value right here at t equals 2 seconds is going to be how much?
It's 9.
It's going to be t, plug in t equals 2. So that's going to be 36. Now, so I at t equals 2 is equal to 36. Now we go over to the next time interval. Go over to the next time interval. 2 is less than or equal to t, which is less than or equal to 4. We have v of t is equal to how much? Minus 9. So then we're going to have I of t on this time interval is going to equal 1 over L, which is 1 over 0.5. The integral from 0 to t of minus 9 dt plus here is where I have an initial condition. What's the initial? Oh, and this integral is, no, it doesn't go from, it goes from what time interval are we on? 2 to t, where t is less than 4. And this becomes I at t equals 2, which is how much? 36. So therefore, this integral comes out to be I of t is equal to 2. Then we have minus 9 integral from that of dt. That's going to give us a t, and that gets evaluated between 2 and t plus 36. All right? So therefore, I of t is equal to minus 18. And then we have t minus 2 plus 36. Make sense? All right? So this becomes what? Minus 18t minus the 18 times 2 is going to give me a what? Plus 36 plus 36. So this guy comes out to equal minus 18t plus 72. So this is now going to start doing this. Like that. So this curve is minus 18t plus 72. Ooh, my. All right. Now, let's find out if I plug in t equals 4.
So it's negative 72, 72,
It goes to 0. Plug in t equals 4 here.
negative 72.
Minus 72 plus 72 gives me? So it's going to go right to there at that point. So now we're going to have 4 is less than t, which is less than 6. We're on this interval. We're going to have v of t is equal to plus 9. And I at t equals 4 is equal to 0. All right? So we're going on these time intervals. What do you think that curve's going to look like? Let's just take a guess. It's going to go up at 18t again.
Yeah.
You're going to get out of this guy. See, again, we're doing this integration was done over here, wasn't it?
Yeah.
So this guy's going to go, I can tell you what it's going to look like. This is going to go like this, and it's going to do that.
And then, yeah, right.
Yeah. What's that?
The y-intercept changes for those other values.
Yes, the y-intercept will change. Yeah, right. Yeah, because now this y-intercept's going to be going way up here. This one went up to 72, right? Take a guess. What do you think that'll be up there?
144.
I got Einstein in the room. 144. Very good. It's going to go all the way up, and it's going to hit this y-axis at 144. Marvelous, darling. Marvelous. Awesome. All right. That takes care of that. All right. That. All right. I think this is the last one. All right. Yeah. Good. Good. All right. All right. So here we have. This is a different waveform. Instead of this is a sawtooth, what we call. So this is V of t. All right, so we have in this case V of t for 0 is less than t, which is less than 1. And this goes up to 5. What's this equation for this curve? 5t. Okay? So V of t is equal to 5t. Okay? And then we have this guy down here. What's the equation of that curve? This is going to be minus 5t, and then you have an intercept down here, right? Where's the intercept at? Minus 10, right? Make sense? All right. All right, so therefore, V of t. Now here, we have an initial inductor current that is 0. All right, so for this time interval, I of t will equal 1 over L, and it's a 10 millihenry inductor, so it's 1 over 10 times 10 to the minus 3 times the integral from 0 to t of 5t dt plus I of 0. And what's I of 0?
You're gonna say 0?
It's given.
Oh.
It's given.
Oh, okay.
Yeah.
Isn't that a positive slope?
Huh?
Isn't that a positive slope?
Yeah.
But it says negative 5t.
Oh, sorry.
No. Why is it negative? Why is it positive 5? It's negative 5t.
No,
Oh, no.
positive 5.
Oh,
Because
It's a positive slope.
Okay.
Even though it's below the
no.
this axis, it's still yeah.
Going up under the axis.
Yep. All right. So this I of t is equal to 1 over 0.2, which is going to give me what? That's 1 over 0.01, so it looks like it's 100, right?
Yeah.
Integral 5t dt, we bring a 5 outside. This gives me a 1/2, which is t squared over 2. T squared evaluated between 0 and t. Right? We're good? So then I of t is equal to 500 divided by 2, 250, t squared. So that takes care of that guy. All right? I got to keep an eye on the clock. Breaky poo? You want me to finish it? All right, so now we're going to have for 1 is less than t, which is less than 2. What is it? V of t is equal to, what is it? Plus 5t minus the 10. All right? So then we're going to have V of t is 1 over L. When we flip that inductor, this becomes, so this becomes 100 times the integral from 1 to t. We're on this time interval, 5t minus 10 dt. I need more chalk. Is that all right? Okay, cool. So V of t is equal to 100. Well, it's going to be 500. The integral from 1 to t of t looks like this is going to give me minus 1,000. Minus 1,000, integral from 1 to t of dt. So therefore, V of t is equal to 500 divided by 2, and we evaluate t squared, gets evaluated between 0 and t, minus 1,000, and this is going to give me t, and that gets evaluated between 1 and t. So this is going to give me 250. Oh, this is not 0, this is 1. 250 t squared minus 1 squared minus 1,000 t minus 1. There you go. Better? Feel better?
So what does that tell us exactly? What can I do with that information now?
Well, again, if you were to, you know, in the end, you will tell me I need that kind of a that kind of a current. Okay? I then have to reverse engineer myself to figure out what voltage is going to give me that. So I have to go through these integrations to figure, you know what I mean?
But aren't things like voltage and current something you can just produce normally? You don't have to do math to get them?
You can go into the lab. We go right across the hallway over there, and we produce voltages and currents that drive hovercraft. But the thing is, as a designer, I have a step-down transformer out there, all right? I got a voltage coming in at 100, or, you know, at 60 hertz, all right? You as a Pico engineer, they will say, okay, you got to drive. Let's say I'm doing a subsystem like down at the Navy Yard. These are the voltages I have coming in. Design me the induction coil that steps them down to run these three-phase motors at 60 hertz at maybe 240 volts, sinusoid. You know what I mean? So you got to go through the calculations.
And that's the equation to do that?
Yeah, we're just exercising that one equation. That's all we're doing, all right? We're just exercising this equation for a whole bunch of different examples.
And I guess my question is, how do you turn that equation into the physical?
Yeah.
Design.
So like that's.
Yeah. Wait till you get to circuits 2.
Yeah.
Oh, you have to
Is that
apply
what
that
you're
to
going
make
through?
it.
All right, Peter's going to take over. Gang, it's been real. I hope to see you all around. You know, say hello. I have to go feed my Miss Curry and Miss Susie. They're getting teppanyaki tonight. Woo! It's been fun. Oh, Peter, here. I don't want to walk out with this. Chalk.
I know.
I know.
You should just move away from the whiteboards.
I know. Go figure.
I'll
Take care.